Hello, my name is Alana Vilagi. I've been working as an intern this summer for the Alaska Center for Energy and Power with the Power Systems Integration Program. The program works to optimize diesel renewable hybrid energy systems for islanded electric microgrids. There are significant opportunities in the state of Alaska to improve the performance of the existing power systems of rural communities. The Demand Response Simulator is the first step in building a power demand management system. Microgrids are characterized by a smaller customer load, are geographically smaller, and demand is less predictable. These isolated power systems are not supplied by conventional interconnected power transmission systems. Rather, electricity is often generated using diesel fuel. One solution to offset the use of diesel is the integration of renewable energy into the microgrid. However, renewables such as wind and solar have challenges of instability and intermittence. Demand response management can provide stability to a grid by monitoring power use with meters and reducing power consumption through the use of switching devices during periods of peak load. Demand response can lower the chance of overload on the grid and reduce the number of outages. Saturn South is an electronics manufacturer based out of Tasmania, Australia, specializing in circuit and appliance level switching and metering solutions. In 2013, Saturn South worked with Hydro Tasmania's King Island Renewable Energy Integration Project to introduce a demand management system to the island. The King Island grid is similar to many villages throughout Alaska. Its customer load varies between 1 and 3 megawatts, relying on a power system of diesel generators, a small wind farm, and flywheel energy storage. Saturn South devices allowed businesses and households to monitor their power consumption and power companies to dynamically adjust total energy demand in the network. The objectives for this project revolve around simulating the control software of a fleet of Saturn South devices by replicating their behavior inside a network. Developing this software specification will allow us to have a better understanding of how to command and control the hardware, as well as identify limitations and scaling issues. This involves profiling the devices by their functionality and attributes, writing separate routines to simulate the device profiles, coordinating the routines to act as a centralized group of simulations, and finally, adapting the software to control the load bank. I devoted most of the summer to profiling the Saturn South devices. For the scope of this project, we looked at the Mini CT meter, the Mini 3-phase meter, and the ESBox LT. I first focused on identifying the similarities among the devices. Determining what features the devices have in common will reduce the effort we'll have to put into our software development later. An important similarity among devices is how they are identified among each other. Each device is identified by an identical routine in the network, and communication among devices is quickly established. Saturn South devices communicate over a Zigbee network, a wireless network similar to Wi-Fi but at a different frequency and within an area reaching up to 30 meters. Part of device profiling was determining the way messages are delivered among devices. For all devices, messages are tested for proper formatting and identified by headers stating their intent of a command, response, or request. When it came to writing routines to mimic device functions, I needed to determine what variables would be inputs and outputs for each device. I tried to limit the number of inputs to maintain program efficiency while still being realistic about the calculations that would be necessary for the device to perform. The ESBox provides the link between the energy services company and the meters by establishing the Zigbee network for the demand management system. Understanding how this device locates meters and retrieves and stores data is essential to profiling the ESBox. Meters must request to join the network, and the ESBox acts to identify and authorize each device. The ESBox is used to manage and organize the network. Commands to the meters are deconstructed by the ESBox, and results are then stored in the ESBox until either requested by the user directly or delivered to a secondary database set up by the user. Meters are used to monitor and control electrical loads. Load switching is performed by an internal isolated relay. The CT meter is designed for use with single-phase loads, and the 3-phase meter can be configured for use with either a 3-phase load or 3 separate single-phase loads. Device functions are organized by intent into groupings called clusters. Clusters common to both meters include the basic cluster, on-off cluster, and the simple metering cluster. The basic cluster is used for device identity features such as location, information about the power source, and whether the device is enabled. The on-off cluster is used for controlling the state of the primary switching element of the meter. The simple metering cluster is used to determine the power metrics. To simplify the profiling, we assumed each endpoint of the device was capable of reading root mean square voltage and current, mean reactive power, and mean frequency. We can then calculate other metrics of interest such as apparent power, active power, power factor, and accumulated energy. Additionally, the CT meter may be capable of performing load control and under-frequency load shedding. This means the meter will open the connecting relay and will not reconnect until frequency is stabilized. Under-frequency load shedding can be important to a microgrid in which generation and demand fluctuates, causing frequency to drop. Decreasing the number of loads on the grid near the time of peak demand means we can avoid a potential power outage and make the way we consume electricity more efficient. I would like to thank my advisors Mark and Luis for their guidance throughout this project, and my project partner Samantha for her enthusiasm and help at every stage of development. Also, a thank you to Tim Warren for his insight and patience. I've learned a lot this summer and couldn't have done it without you.